Hey kids, Smath here. As promised, here's our second installment on colligative properties. And I explained the concept last time and gave you a couple of calculations with it, but we were running a little short on time. So right now, I'm gonna hop right into it, give you another couple of examples here. Let's see how to do these calcs. The first one of these is pretty straightforward. Now we've been given a bunch of data up top. Right up here, you will always be given boiling points, freezing points, KBs, and KFs. These will always be given. About the only thing I'd really like you guys to bring to the table maybe, boiling point to water is 100, freezing point to water is 0. But you know, I'd even give you that. You just got to be able to use it. So the question asks us, what are the freezing points and the boiling points of a solution that contains 6.5 grams of ethylene glycol, this is antifreeze, and 200 grams of water. So we've got the answers. All we got to do is find a way to make those match up. So the first thing I want to do is I want to calculate the molality of this. So C2H6O2, if I add up the molar mass of that, that's going to be 62 grams per mole. So if we've got 6.5 grams of that, 62 grams per mole, I'm going to have 0.105 moles, and that's going to be in 0.200 kilograms of water. So my molality ends up being 0.525 molal. I just took that 200, turned it into kilograms, 0.2 kilograms. Okay, so now let's find the change in boiling point. Delta T in boiling is going to be 0.51 degrees Celsius molal times the molality, 0.525. And in this case, this is very carbon-based, so its I is going to be 1. So if that's the case, our change in boiling is 0.267 degrees Celsius. It's water, so it normally boils at 100. So the boiling point to this solution, 100.267 degrees. That's my boiling point. Now let's do the same thing with the freezing point. Delta TF, now we use the 1.86. Same molality, it hasn't changed, 0.525. And the same number of ionic particles. That ends up giving a freezing point of 0.977. And in this case, it's going to be 0 minus 0.977, or a negative. That's my freezing point. So basically, what did we do here? Whoops, I missed my negative sign, but that's all right. Basically, we found out the molality, okay? Then plugged it into KMI, found out the change. We added that to boiling. We subtracted that from freezing. That's how we got both of those. That was a two-part problem, all stuffed into one pretty tight. That was a little bit rough. We have the same thing coming up now, where we've got 55 grams of glycerol, C3H6. I checked that out. That molar mass, 92 grams per mole. So let me do that real quick. Blow this up a little bit. So we got 55 grams, and it's 92 grams per mole. That's going to give me 0.598 moles in, watch out, we got 250 grams of water this time, so 0.250 kilograms. And the molality of this solution is 2.39 molal. Same thing now. We're still in water as a solvent, so we're still going to use 0.51 and 1.86. So here's what it looks like. Come on over and say delta TB is 0.51 degrees Celsius molal times 2.39 molal. And once again, C3H5OH3, very organic, very carbon-based. Therefore, I is going to be 1. I'm going to get a change in boiling of 1.22 degrees. Add that to 100, and we're going to get a boiling point of 101.22. That's what the answer said it was supposed to be. Let's check out the freezing. Same thing's going to come into play. Delta TF, the change in freezing point, is 1.86 degrees Celsius molal. And it's still 239 molal. That's not going to change, nor is the number of particles. And that's going to give me a freezing point of 4.45. In this case, it's 0. The freezing point of the solution is 0 minus 4.45, or a negative 4.45 degrees Celsius. Close enough for what we got. So far, we're 2 for 2. We add to the boiling point and we subtract from the freezing point. The boiling point always goes up, freezing point always goes down. Now, these two are the same type of problem. Now, what happens when we have an ionizing solute? Now, this is going to break apart, and I is not going to be 1 anymore. We're going to have to look at what that I value actually is. So what I've got is 1.25 moles of calcium chloride and 1,400 grams of water. Okay, first thing we got to do, break that, get that molality. That molality, pardon my yellow, that molality is going to be 1.25 moles per 1.400 kilograms, 0.890 moles per kilogram. All I did, the problem gave me moles already. I just had to turn 1,400 grams of CaCl2 and of the water into 1.4 kilograms of water. It's got to be in kilograms. So now I've got the molality. What do we do with that? Well, it's a boiling point problem. So delta TB, and it's still in water. Water is my solvent. I think we still have one more with water. Then we're going to have one that doesn't use water for a solvent. But right now it's going to be 0.51 times 0.89 molal. But now look at this CaCl2. That's Ca from all the way over on the left and Cl from all the way over on the right. That's going to dissociate. That's a very ionic compound. That's going to break apart into 3 particles here for us. So now we go 3. And if we munch that together in our calculator, you're going to get a change in temperature of 1.36 degrees. And since it's boiling point, it's going to be 100 plus 1.36. 101.36 degrees Celsius. That's how we get that. It just is the same as what we've been doing, but we had something that was ionic and it was going to break apart on us. Now we're going to do one, same type of problem, but now it's a freezing point and they didn't give us moles. So now we have NaCl. That tells me I equals 2. All right, what we need to do first, get that molality, 25 grams, 25.5 grams, 58.5 grams per mole. Now you start to see why moles were so important. They're in every calculation in chemistry. So take that and divide it. I'm going to get 0.436 moles, and that's in 500 grams of water. That's got to be in kilograms though, so I'm going to make that 0.500 kilograms. I'm going to get a molality of 0.87 molal, little m. All right. Now we got to find freezing point. It's still in water, so I can use the KF of water. So delta TF is 1.86, excuse me, degrees Celsius, molal, 0.87 molal, and now it's NaCl, 2 particles. Really doesn't have a unit on that. That's going to change the temperature, 3.24 degrees Celsius. It's freezing, it's water, so the freezing point here is really just that. How do we show it? We show 0 minus 3.24, which is going to be a negative 3.24 degrees Celsius. That's how I get that freezing point of that solution. I'm Smath. I've got a couple more of these to do for you in the next video. I just wanted to show you what basics look like. I hope this video helped you.